Whew! Right, we've done a lot. If you haven't stopped and had a coffee break, at least one by now, please do so. But you're on the final stretch. There's 2 more bits to do, and they're both a lot easier than what you've just done. So this is now getting your final error. I keep saying error. I should really refer to them as an uncertainty, but an uncertainty's just got too many vowels when you keep having to say it. So final error uncertainty. Right, so what you've got now is, so you have a value for row, your answer, which is meaningless at this point because we don't know how bad that is. We don't know how big the error is. Without the bit we're about to do, that value is useless. Is it quite precise? Is there a big, how bad is it? How useful is it? So we've got a value for row. We've got a graph with a straight line, and hopefully we've got some points, and we might have some error bars. Or if nothing else, we've got some errors at least on the axes. At this point, it's easier if you can get error bars on the graph because it makes this next bit a little bit easier. But the chances are, a lot of the time, you're going to find your errors are too small. It's worth noting at this point, looking back and reflecting on all that error calculation that you've just done, this doesn't take into account anything which doesn't really come from your collection of raw data. So it doesn't take into account, obviously, errors that you didn't realise were there. But that plus or minus that you do in your raw table obviously is vitally important for feeding through to the size of those error bars. Now here's what you do for the final bit, error-wise anyway. We've got to do a comparison yet, but that's even easier. Think about how you got your resistivity. Remember that you did your resistivity was gradient multiplied by area. Okay? Much in the same way that we've just looked at, resistance was voltage or potential difference over current, and you had to do the percentage error in the voltage and in the current, add them together, and that would give you your percentage error in R. Of now you could work out the plus or minus. Well, it's the same thing. To get the error in resistivity, we need the error in gradient plus the error in area. So delta rho as a percentage equals error in gradient, remember that's n, as a percentage, plus the error in A as a percentage. At least for this one, you've only got to work all these things out once because you've only got one set of data now. It's all from the graph. It's not for every row in your table you've got to do it, so this is a lot easier. Okay, so there's 2 bits to this. 1, 2. Let's look at bit 1 first. A max or min gradient. Excuse me. Right. What you've got is boom, 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 boom. Error bar, error bar, error bar, error bar. Hopefully you've got 6 bits of data. Error bar, error bar. You've got a line of best fit, which is straight, and that's the original. That gives you M, which in turn gave you your answer row. Alright, here's what you do. You now put on the least acceptable line of best fit. That is not an acceptable line of best fit, it's just a random dash on a page. Where you've got error bars, this is easy. You go from the bottom of one set to the top of the next. Or you could go from the top of one set to the bottom of the next. I'd go with whichever gives you the sort of worst answer, but you only need to do one. So draw, I'm going to go with a thicker pen, draw a max or min. You don't need to do both. You can take both and you can average them if you want, yeah, nothing wrong with that, but you don't need to do both. It's fine just to do the one. Draw a max or min line of best fit. This gives you a max min gradient. So, e.g., let's say original gradient was, let's go, I'm just going to pick nice easy numbers. Let's say the original gradient was 2. Let's say that the max gradient from my maximum line of best fit was 2.1. I can, from that, get my percentage error in gradient. Do the difference, so 0.1 over 2. Difference over original, obviously times 100. So 0.1 over 2 times 100 gives us obviously 5% error. That's pretty big. Now here clearly you can see the smaller the error bars, or the less scatter in your data, the closer that extreme line of best fit. So let's label that as, would be a max line, because it's giving me a steeper gradient, that's why it's a max line. The less scatter I've got, the smaller my error bars, the closer that's going to be to those points. So the smaller the percentage error. Literally, in this case, this is the percentage difference, okay, between your maximum gradient and what your gradient originally was. But that gives you number 1. Ba-boom. Okay, for area, it's exactly the same as any other calculation. So for number 2, look at how you worked out the area. This is where you're glad that it didn't work out the radius and you worked out from diameter instead, because you know what, it's just easier. Actually, it's technically, I don't think it makes much difference, but it's less faff. Area is pi d squared over 4. So, what is the percentage error in A? Well, it was d times d, so it's the percentage error in d plus the percentage error in d, or, as it's squared, obviously, it's just 2 times the percentage error in d. So go back to your diameters. Look up your diameter. Let's say your diameter average is your mean, obviously, diameter. You have repeats. How do you get the error from some repeats? Standard deviation. And then standard error is the standard deviation divided by root n. So if you've done 6 different diameters, you can get the percentage, you can get the error in that, work that out as a percentage, and then double that gives you a percentage error in A. You can add those 2 percentages together now, and that will give you a percentage error in resistivity. So the final thing to do, number 3, so get percentage error in A. So final thing to do, 3, add percentage error in A plus percentage error in gradient gives you your percentage error in your resistivity. So work it out. Do not leave it as a percentage. You've done all that hard work, really annoying, to then throw it all the way at the end. Get an absolute error. Get an absolute error in a row. So let's say your percentage error comes out at 6%. So work out what 6% of your value was. If total error is 6%, calculate 6% of your resistivity value. And this is the big thing. This is what lots of people don't do. Remember, the whole point of this experiment was to give a p-value, a resistivity, a rho value, sorry, not p-value, a rho value for resistivity. So give it with its error. Quote, final answer, and its error. I'm aware that this scribbling is the sort of handwriting of a madman, but put that down to many, many things. So, for example, you would give your resistivity as, like really obviously written somewhere, really obvious, resistivity as 4.31 times 10 to the power of 9 pascals, plus or minus, whatever it is, 0.5 times 10 to the power of 9. But you know what? That's not very tidy. So perhaps would be neater to go 4.31 plus or minus 0.5, probably should be 0.50, boom, boom, times 10 to the 9 pascals. Or you could say 4.31 plus or minus, so that the plus or minus is in the same unit, that's the point. Same unit, same number of significant figures, same level of precision. Instead of times 10 to the 9, gigapascals, or whatever your value is. I'm not going to give you that. You can look it up. Give your final value in a really obvious, like, I have no problem. You've done a lot of work to get to this point, so put some flaming gold stars next to it or something. Put it in a box, highlight it, I don't care, underline it, write it in red. I don't mind, but make it stand out. Because this was the point of your experiment. So I don't want to have to sort of look through a load of scribbled notes and calculations to get a value for p that's in there somewhere, and then an error that's in there somewhere too. It kind of makes it look like you didn't really know what you were doing. Writing it, oh, this is what we were after. I know that you were clear from the beginning about what it was you were up to. And it's stupid, but it really makes a big difference, so make sure that you do it. Right, that is almost the end. That's all the hard work done. The next bit is very, very easy, and it's just about finishing off.